And what was the title of the one before? I didn't even.
I don't know.
Hmm.
I would.
I remember he wrote on the board like he must have left, like typo on something, but then I didn't even find a typo.
So yesterday, I went to
I guess we're always small. Okay, so we're gonna get started. Because we are. All right, so we're going to move forward into the last of our periods for the Precambrian eon today. So we're going to be talking about the Proterozoic. So before we do that, I want to talk a little bit more about what's going on with the Earth's climate at this point in time. So over the period of geologic time, Earth has experienced at least 5 major ice ages, like really, really major. We're talking, as you can see at the top of the slide, this is the snowball Earth theory, like literally turning the entire Earth into a giant block of ice and snow. So 3 of these glaciation events, these ice ages, happened probably during the Precambrian eon. So we talked previously last week about the Great Oxidation Event or the Great Oxygenation Event. Sometimes you'll see it referred to as like the oxygenation disaster or catastrophe because it created a really major change in the environment that early life was developing in. We briefly mentioned that the replacement of methane in the Earth's early atmosphere with carbon oxygen removed that greenhouse gas, therefore decreased the temperature of the Earth. And this is probably what caused the Huronian Ice Age. Maybe arguably there's disagreement, also the Pangea. We saw those dips, those banded iron formations, really clustering around about 2 billion-ish years ago when we're looking at their formation. Okay. So those are not actually what I want to talk about right now. We want to talk about the Cryogenian, which is, I think, maybe the most famous of these major glaciation events, these ice ages. So during the Cryogenian, we have the creation of what we think of as a snowball Earth. And to understand that, I want to learn a little bit about why we don't have such massive temperature changes now. So the Earth theoretically has kind of a thermostat. We have some mechanisms that kind of buffer out major temperature changes, one of which has to do with weathering and volcanoes. So volcanoes, which we know there were a lot of during Earth's formation, spew all sorts of things into the atmosphere, including a lot of CO2. Okay, so this tends to warm the Earth on the whole, because CO2 is a greenhouse gas. But then we tend to have this CO2 basically ending up in the ocean. Okay. So the CO2 ends up in the ocean, falling to the floor. And the other thing that's happening is that CO2 is being removed from rock by weathering, ends up in the seafloor through subduction. Basically, the rock ends up underneath the Earth again, where it can then come back again as a volcano. So this sort of cycle of CO2 can pull the temperature back down when it goes up from volcanic eruptions. Yep. So around the time of the Cryogenian, we do have a breakup of a massive supercontinent. So a supercontinent is like all the continents were smushed together. People have heard of Pangaea, but Pangaea is actually a more recent supercontinent. So this really early one that we're thinking about way, way back around the Cryogenian is called Rodinia. So here we can see a map of Rodinia around 1 billion years ago. So it's around 1 billion years ago, and then it starts to break up due to massive explosions of volcanoes. Right, so this supercontinent is breaking up. It's spewing lots of gas into the atmosphere, which you would think would warm the Earth. But part of what's being produced as these endless volcanoes essentially are exploding is a bunch of basaltic rock, which starts trapping that CO2 like crazy. So as it traps the CO2, that brings the temperature down and ends up bringing it really way, way down. The other thing that happens is these volcanoes are spewing out sulfur. And these volcanoes aren't like a normal volcano. They're going and going and going for a really, really long time. So what happens is the sulfur would usually sort of rain out down onto the earth. But the sulfur is staying up there because there's so much of this and it's cooling the atmosphere more and more. So this is how we start to end up with this snowball Earth situation. The continents are breaking up. We have these volcanoes exploding, and while they are emitting CO2, they're also emitting the sulfur, and that CO2 is getting trapped in the salt, and the usual Earth thermostat CO2 cycle is not happening. So the polar ice caps start to freeze over, and as they freeze, they end up forming, right, like ice is white, snow is white. They end up reflecting a lot of the sunlight coming down because there's so much ice. And this cools the earth further until it is a giant snowball eventually. And we think it was actually a giant snowball because we can see in the rock record, the geologic record, evidence of this glaciation everywhere, not just at the poles, not just in any specific location. For a while, they suggested that maybe the Earth was tilted different, and that's why we were seeing evidence of glaciation around the equator at places that are typically warm. But really, we see evidence all over of this snowball Earth. Okay. So the snowball Earth formation, light is being reflected, everything's really cool. This means this stops the CO2 cycle in the ocean. And so then the volcanic gas starts to build up even more. Then we go through a hot period, and this actually we think happens twice essentially. This going really cold, then eventually the CO2 building up, going really hot, then diving back down to really cold. So this is what is happening at the end. At the end of the Precambrian in the Proterozoic. So when I say that there's evidence of this snowball Earth event across the Earth, one of the major things that you can look for are something called drop stones. So in the seabed, we're putting down sediment layers. You can see those layers, you can take those layers in ways that we've discussed previously. But during this time period that we're talking about, we end up seeing these huge, just kind of rocks embedded in these layers like this. So what we think is happening is that this was as those ice sheets were melting. So as the snowball Earth was starting to warm back up, these melting icebergs with deposits in them started literally dropping stones onto the ocean floor, which went through a couple of the layers and then ended up embedded there. So that brings us into the life we're going to be talking about in the Proterozoic. So we talked a bit about oxygenation. We talked about our prokaryotes becoming eukaryotes. We talked a bit about multicellular life. We have the snowball Earth in here now. We talked last time about ozone forming after the oxygenation. And now we're going to be talking about Ediacaran, organisms. And I say organisms because for a while there was an argument about exactly what they were, whether they were plants, whether they were animals, whether they were microbial communities. So we see in the end parts of the Precambrian, in the end parts of the Precambrian, during the Ediacaran period, all sorts of kind of soft-bodied fossils appearing around the globe. So here we have some of those fossil localities listed out. And here we have a little bit of a timeline here. So we're looking at the Cryogenian starting out. We can see there's maybe another glaciation event in here. We can see I think they listed the volcanoes somewhere on here. It's listing the ages of some of these assemblages that they're looking at before the Cambrian, which is going to start our Phanerozoic. We'll talk about that in our next unit. Okay. They're going to call them Ediacaran biota because we know they're biological at least. So we have all these soft-bodied organisms that start appearing. So here's some of our fossils that we can see. They're basically kind of imprints for the most part. And here's an artist's rendition of what they might look like, which may or may not look normal to you depending on how familiar you are with the ocean floor. But these are not body shapes that we see today, really. These, the morphology of these creatures is really different than what's in our oceans now and than life on Earth now. Okay. And because it's so old, they've done some arguing. So one of the things you might not have realized about that previous picture is the scale. So one of the Ediacaran organisms that we can see is something called Dickinsonia. So this maybe looks like a little seashell kind of looking thing until you realize that this is 1.4 meters long, so like size of a person. And we're thinking about 500 million years ago, so fossil deposits like 567 million years ago. And what we're looking at here is essentially a fossilized death map. So we'll talk about this fossilization process in a second. Before we do that, I'm going to ask you at the end of today to look into a number of different of these Ediacaran organisms. So I'm going to make sure that we define some of the words for things that I'm going to ask you to look for. So one thing is morphology. So when we look at the morphology of something, we're thinking about its size, shape, and structure, so kind of its anatomy. So if we look at one of the examples of Dickinsonia, this is one of the ways they tried to figure out whether it's an animal, a plant, maybe just the sign of like a worm moving. They looked at the shape of these fossils. Okay, so here we can see they've reconstructed the front here as the head. Then they think that these are little subunits branching out here. I thought the growth was coming from the back of this organism. They decided they thought that there were digestive pockets kind of bordering these different subunits. You can see that there are descriptions of the shape of the fossil as well. So we can see impressions of kind of contraction. We can see rounded edges here. We can see infolding kind of some of these subunits. One of the cool things about Dickinsonia is they were pretty sure that it was moving across the seafloor. They're pretty sure from the way they were seeing these impressions kind of shifty around the edge, there was movement. So to figure out whether this was a plant, an animal, what was going on here, there's a pretty recent study actually that looked in the fossil, took little tiny bits of these fossils to look at signatures of the lipids that were in them. So DNA denatures and decomposes pretty rapidly, but lipids actually stay around a lot longer. And there are different ones in the cell membranes of different organisms. So algae tend to have stigmasteroids within their membranes, while animals have cholesterol essentially in that, embedded in that phospholipid bilayer of the cell. So recently, there's this PhD student, I think he now has his PhD, who went in, took a little bit of these fossils that he found in cliffs in Russia, ground them up to see what lipids were there, what kind of steroids there were. So both below and above, they saw a large proportion of the steroids remaining in the rock were these stigmasteroids. So indicating that before and after, you're seeing a lot of essentially algae. But right in where they had the fossil, it's like 90% these cholesteroids, which is really strong evidence for the side of the argument that says that Dickinsonia was one of the first animals, or one of the predecessors to our animals, which we also at this point in time refer to as metazoans. So it was interpreted as a metazoan, an early animal. So another thing that I'm going to ask you to look for is a little bit about phylogeny. So we mentioned phylogeny has to do with looking at evolutionary lineages. So we're looking at tree of life, basically. So a phylogenetic tree, this sort of branching tree here. So we have outgroups on phylogenetic trees, so not the thing you are studying. So here our outgroups would be plants and fungi. Okay, so our metazoans start to be somewhere around here. You can see that the metazoans have many groups within them. So there are lots and lots of different types of animals, not just the ones that we think about now. And if we're including our Ediacaran biota in the metazoans, we're going to have even more strange groups within this larger clade. So that's a phylogeny. Okay. Finally, taphonomy. So taphonomy is basically the study of fossilization. So when we're looking in our geologic record, as far back, we're looking for fossils. We don't have, obviously be dead, but we don't have really decaying biologic material anymore. So Dickinsonia is mainly fossilized as a death mask. And to understand how we think that works, we're going to go back to this image of the stromatolite. Before we were talking about the stromatolite as essentially microbial mats that were growing in layers with deposits of mud and minerals between them, and then growing more and more layers on top. So when we see these Ediacaran biota, they don't have bones, they don't have shells, but what we think is happening and why we actually have fossils of them is that they're essentially getting jammed between these microbial mats. So in one of these layers, as the mud is depositing, we have like one of these Ediacaran organisms kind of falling on top of a microbial mat and then getting covered over with the new layer. So as it gets covered over with the new layer, we end up with this shell that the organism didn't have in life, but that's being created by this growing microbial mat above and below. So in general, when we talk about fossils, we think about some part of the organism being preserved. So when we're thinking about Dickinsonia, we're thinking about this death mask, thinking about it as essentially kind of like an imprint. We don't have like the inside of the Dickinsonia left. So the fact that they found these lipids is kind of cool and crazy. So a fossil can be pretty much anything, can be an animal itself, can be a little bit of pollen, can be something stuck in amber, really any evidence of pre-existing life. Okay. So we can have body fossils where we have the entire body preserved. We can have trace fossils, which are going to be like imprints. So like dinosaur tracks count as trace fossils. And chemicals would also count as fossils as well. So these biomarkers that we're seeing essentially. And here we have some pictures of dinosaur tracks. I went to a paleontology conference where they were reporting on studying dinosaur tracks, and some of the experiments they do for these are crazy, right? Fossils, we don't have all that much information on, and you wouldn't think they could do that much with a track, but they're like sending chickens running through all different kinds of mud. They're building robots that walk in weird ways. They're doing all sorts of things to try and reproduce these kinds of fossil evidence. And it's really funny sometimes to see what they come up with. So trace fossils are cool and useful because we can try and infer behavior of organisms in the past when we have like records of their movement. So just like tracking animals, I guess. Then we have modes of preservation that preserve like actually original body parts. So we're going to have basically mineral deposits trapping organisms within layers of sediment. So we have silica, we have various calcium containing molecules that do this. So we can either end up with fossils that are preserved in 2 dimensions. So we end up essentially with our organism getting crushed and flattened between layers. And we may end up with mostly what just looks like an imprint, or we can actually have mummification and 3D preservation. So we sometimes call those body fossils when we have actual original material from that organism left. Okay. A couple more just like fossil words. So a cool new vocabulary term for fossils is permineralization. So when we're talking about fossils being preserved with their original body parts, actually, essentially a lot of this tissue has kind of become rock. So when we have permineralization happen, we have our original material, and then we essentially have minerals seeping down through groundwater and slowly taking over all the space within the fossil. So this is going to happen through materials like silicon dioxide, calcium carbonates, other things going on here. We're going to end up with basically just like a little bit of preserved cell. So we'll have maybe some membranes and stuff. And then the spaces around will have filled in with these minerals that crystallize and help us keep that shape. This is slightly different than petrification. So if you see like petrified wood, we actually don't have any of the organic mineral left at all. So in addition to filling in the kind of spaces that have decayed away, we actually replace the original material in full, including those like walls of the cells and stuff. So those petrified, quote unquote, fossils would lack any of the original organic material. So what we're going to do today, while we're talking about phylogeny, preservation, this part of our geologic time record, want to grab essentially some data so we can also think a bit about adaptive radiation into growing ecological niches. So I picked a list of ediacaran organisms that I think you should be able to find some information about. So what I want you to do is go through, you're gonna make a couple slides, doesn't have to be anything complex or intense, that we'll talk about on Wednesday, so we get an idea of the breadth of what was around. So I want you to find some dates of appearance in the fossil record, so like the time period we're talking about. I want you to look a little bit at the distribution. So by that I mean like their range, like where are we finding these fossils? You can either reference like locations today, or if you find any information about like how deep they would have been in the ocean, things like that, that would be helpful information to have as well. So tell me a little bit about their morphology, so their shape, the ecological relationships you can find, so what they were eating, what they were related to, so possible phylogenetic relationships. And it's fine if you use like popular sources for most of this, but I do want you to find descriptions of at least 2 actual papers that are discussing this organism. So let me know what questions they were looking at and what kind of evidence they're reporting on as relates to your organism. And then we'll briefly go through these on Wednesday. Yeah, that's basically where we're ending for today. That's our activity for today. And before Wednesday, we have a test coming up on Friday, I believe, on our schedule. So before then, I'll go through and I'll make you like a little outline kind of study guide thing to kind of focus us in on what you should be studying for that. Sound good? Cool.
What is it?
Mhm.
Is it gonna be like mostly like multiple choice, or how is it gonna be like the format of it?
Yeah, mostly multiple choice, a little bit of kind of short answers.